Hello again. So, still talking about some mathematical integration. Today, and I'll just give you a bit of a warning as well, is going to be lots and lots and lots of explanation. So if you're finding the explanation quite hard going, in the notes, the main take-home points I've highlighted in red. So the objective here, I hope you actually try and understand the main results in red. But it's going to be about 20 minutes of explanation after the warm-up. So just a heads up, it's going to be quite hard going, but if you can get your head around it, it will massively help you appreciate the results rather than just knowing them by rote. So try and keep the video if you can, but just a heads up, it might get tough going and quite slow, but that is a deliberate thing I'm doing. Anyway, I'll come to that in a moment. Right now, here's the 4 main warm-up questions for you, which you should have come to expect by now. So pause the video now, jot them down, or do them on paper if you've got a printout of it. When you're ready, press play and we'll go through the answers together. Okay, so here we go. Question 1. We've got a particle of mass 2 kilograms moving in a plane, just means in a surface, under the action of a single constant force of F newtons. At time t seconds, the velocity of P is v meters per second. At t equals 0, v is minus 5I plus 7j, and when t is 3, the velocity is changed to I minus 2j. So find in degrees the angle between the direction of motion of P when t equals 3 and the vector j. Okay, so what you need to remember is that, whoops, that's one of my little apps there, get rid of that. I goes along, and so I is a unit vector going in the direction of x. That's not quite right, apologies. So that's I, which goes along, and you need to remember that j goes up. Okay, so j is like going in the y direction. Again, I just knocked that off ever slightly. There, that's what I mean. So we want the angle in between j and the velocity when t is 3. And so what we're wanting here is the angle in between j goes vertically up, and the velocity when t is 3. Now when t is 3, we've got the velocity as I minus 2j, and so that's 1 unit in the I direction and 2 units in the negative j direction. And so this is going to be something like this. So 1 along, 2 down. So it's going to be something like this, and it's going to be this angle here from j going down like that, where this is the velocity vector. So just to add a bit more detail into this diagram, if I just do a dotted line across like this, we can hopefully see now that this is going to be a right angle, and this here, if I just think about in terms of a right angled triangle, I minus 2j, so that's 1 and 2. And so this angle here, if I just colour this in yellow, say, the required angle is going to be 90 degrees here, plus this angle too. So this angle we can use simple trig for. We know that it's a right angled triangle with a opposite of 2 and an adjacent of 1. So we can use the tan function. So it's 90 degrees plus tan minus 1 of 2 over 1. Essentially tan minus 1 of 2. So we can do this to 3 sig fig. So if we get our calculator, our trusty class whiz like this, and do 90 plus shift tan minus 1, 2 divide by 1. I know I could have just typed 2, but why not? That gives us to 3 sig figs 153 degrees. So there we go. Question 2. From question 1, find the acceleration of P. And so this is actually a SUVAT question. If I just nip back to question 1 just to show you for a moment, what we have here is we are told that we need to work out a acceleration. Well, we're told it's a constant force, okay? Constant force implies constant acceleration, assuming the mass doesn't change. So constant force, constant acceleration, so it's a CVAC question. We can actually use here v equals u plus at. However, we're talking about vectors, and so the vector form of this CVAC equation is vector v equals vector u plus vector a multiplied by t. If we rearrange this, we get that the acceleration vector is going to be v subtract u all over t. And so going back to question 1, v was I minus 2j. Minus what u was? Well, u was minus 5i plus 7j. And all of that divided by t. Now, the time frame which is elapsed is 3 seconds, so we can divide all this by 3. So simplify this on top. I minus another 5i is 6i. Minus 2j minus another 7j, that's minus 9j. All of that divided by 3. That gives us 2i minus 3j. So that's the acceleration vector for this particle. Question 3, differentiation by first principles warm-up. We're going to use this and warm-up question 4 for later. So let f of x equal x squared. Prove from first principles that the derivative f dashed of x is 2x, and we're given here the definition of finding the gradient function. So we just plug in where h goes towards 0, the change in the function value divided by h. So we can use this now. So f dashed of x, whoops, not what I intended. Just undo that line for a moment. Okay, so f dashed of x is the limit as h goes towards 0. Now it's going to be f of x plus h. Now the function here is x squared, so that's going to be the change of x plus h all squared minus f of x, well f of x is x squared, all of which divided by h. That's the same as the limit as h goes towards 0 of this. So x plus h all squared gives us x squared plus 2xh plus h squared. And then we minus off x squared from this. Again, all over h. So you get a bit bored of writing lim h arrow 0 after a while, but it's worth doing, it needs doing. So if you look at the top, the x squared at the beginning cancels with the x squared at the end. And so we just end up here with just 2xh plus h squared all over h. So this will now cancel off. So we've got a h on the numerator and on the denominator, so we can simplify this. That's the limit as h goes towards 0. 2x h over h just gives us 2x. H squared over h just gives us 1h. So the 2x is independent of h, so that's going to stay as it is. But as h goes towards 0, this h term here is going to vanish. So we're just going to be left with 2x. Therefore, the gradient of the quadratic y equals x squared is just double the x coordinate on that curve. That tells you the gradient of the tangent for any point on the curve. Whatever the x coordinate is at that point on the curve, double it, that's your gradient of the tangent. Finally, question 4, find the equation of the curve with derivative 2x that passes through the point 0, 0. And so we know that the derivative, dy by dx, is 2x. So therefore we can find y by integrating this with respect to x. So if we integrate 2x, we take the power up by 1, so 2x becomes 2x squared. We then divide through by the new power. So 2x squared divided by 2 just gives us 1x squared. So we just get x squared plus c. In fact, because we don't get to have any limits to put on, we can actually leave this actually without these squared brackets. Whoops. So it's just actually x squared plus c. So now we've been told a point that the curve goes through, so we can substitute this in. So we're told that when x equals 0, y equals 0. So substitute those values in. So 0 equals 0 squared plus c. In other words, this constant of integration must be equals to 0. So therefore, y just equals x squared. So importantly, warm-up question 3, if we differentiate this, we get 2x. When we integrate 2x back again, we end up with y equals x squared, assuming we know a point on the curve that is. So integration and differentiation undo one another. If we know the derivative function, we can integrate the derivative function to get the function itself back again. In other words, we're going to mention this later as well, f of x is the integral of the derivative function with respect to x. Okay, so that's warm-up done. And now warn you, what's coming up now is a fairly thorough, hard-going explanation of how differentiation and integration work. If you stick with it, you'll get a lot out of it. It is hard-going. You might need to pause the video, replay bits and pieces, but just a heads up, this next bit is going to be quite hard-going, okay? So here it comes. So now, massive point I'm going to try and make here. We're going to try and link what we've done before with differentiation to integration and areas under curves. So it's going to be a lot of explanation this, maybe about 10 minutes or so. But first of all, what I want to do is to just take you back to the earlier work we did when we were talking about the tangent function. If you remember, the tangent function we defined as being f dashed of x, which is the same as dy over dx. So the way we did this is we take 2 points on a curve where the x-coordinate is just x, the y-coordinate is f of x, in other words y is f of x, and then another point slightly on where the gap between the points is h. So the second point is x plus h, and then the function of x plus h. And then we consider the effect of letting h tend to 0, make h go closer and closer to 0, like we have here in this diagram. And so we can see the 2 different points for x and x plus h, and the corresponding change in y, when x is x, y is f of x, where x is x plus h, the corresponding y-coordinate is f of x plus h. So if h is small, then we can see that the gradient of the tangent at x here, dy by dx, is approximately equal to the change in y, which is f of x plus h minus f of x, this bit here, divided by the change in x, which is h. So this approximation is going to become more and more exact as h gets closer and closer to 0. And so this point here gets closer and closer to the point x. And so these 2 different points, from which between we calculate the gradient, becomes closer and closer to the same point. And so f dashed of x is the limit when h goes towards 0 of the change in y divided by the change in x, and that instantaneous change is dy by dx. And I'm going to call this result a here, so we can refer back to it later on. In terms of seeing this a bit more visually, this limit of h approaching 0, I do have as well a little graphic for you here. So imagine this is the change in y, and this is the change in x, as the change in x goes closer and closer to 0. The tangent line is this blue line. The red line is the approximation. As you can see, the red line gets closer and closer to the blue line as h shrinks down to 0, until eventually the red line becomes the blue line in the limit that h goes towards 0. In other words, the gradient becomes the exact gradient of the tangent at x. So just carrying this forward, we also saw from example 3 and 4 in the warm-up, and from the notes in chapter 13.2, if you've got f dashed of x, which is dy by dx, then y is the integral of f dashed of x with respect to x. And so we showed this here where f of x was, so y was x squared and f dashed was 2x. So refer back to warm-up questions 3 and 4 for a particular example of that. We're going to use this result later as well. I've called this result B. So another way of thinking about it is we had here h as the difference between the x values. I'm going to call this change from one point to the other as delta x. Well, delta x is just something which is pretty small. And delta y is the corresponding change in between f of x plus delta x and f of x. And so what we can say here is that the horizontal distance, as I've said, is delta x, the corresponding vertical distance is delta y. In exactly the same way as before, as delta x approaches 0, just as h approached 0, these two different points will begin to merge into one, and the gradient of the line connecting the two, which is delta y over delta x, becomes the gradient of the tangent at that precise point x. So in other words, as delta x tends to 0, delta y over delta x goes to dy over dx. And in a very sort of babyish sound of way, but it's actually a very powerful sort of thing to notice, these deltas become d's. So this is the approximation, the deltas. The exact limit, the calculus limit, is dy over dx. So you might be thinking here, well, how does all this relink to areas under curves? How do these tangents, how do these results, A, B, and C, relate to integration? Well, we're going to draw some parallels between these results and then make a leap forward in terms of integrating areas. So just have in the back of your mind results A, B, and C from here and previous. So let's now imagine area under curves. So we've got a diagram here. So we've got a curve starting over here, and then a blue area to the right of the yellow area. I want you to consider defining into existence an area function of a curve. Capital A brackets x, where that is the area function at the particular value of x. So A of x is the area beneath the graph of f of x between 0 and x. So consider we just wanted to think about this blue region here. Okay, the area of the blue region is approximately equal to this width of the strip h multiplied by f of x. Okay, where f of x is the height. So if I just show you that here, so f of x is the height of the strip. So I'm not saying it's exact, because obviously we have this blue area on top of the rectangle, which means it isn't exact yet. But it's about equal to the area of this blue rectangle. So this blue strip isn't far off being the area of the blue rectangle. Now the exact area in terms of this area function would be the area in terms of this area function. So the exact area of a blue region would be the area function of x plus h, which would mean all of this here. But of course we wouldn't want a of x. So the blue region alone exactly would be the area function of x plus h subtracted away the area function of x. That would just leave us this blue strip. So moving on, you can therefore conclude that this rectangular area here, h multiplied by f of x, where again, just drawing in, this is f of x, that's going to be approximately equal to the exact area, and this exact area, using this area function, is the area function of x plus h minus the area function at x. So we can manipulate this slightly. So if we divide through by h, this gives us that f of x is approximately equal to the area function of x plus h minus the area function of x divided through by h. So the area here is the small blue area above the blue rectangle. But I'm going to show you in a second, as h goes towards 0, this area also goes towards 0 as well. So the relationship becomes exact. So if you look here, the error between the rectangular approximation and the exact area is this area here above the curve. So it's not too big, but it's obviously noticeable. But if I imagine this h distance here becoming smaller and smaller, look what happens to this curved area above the rectangle. That's definitely smaller. Smaller still. Smaller again. 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 And again, until this tiny, tiny white strip here is very close to being the rectangular area you might draw by, for example, using a pen tip and doing a straight line with a pen. So it's almost exactly a rectangle. You can maybe see here a white pixel at the top, which is negligible. So that hopefully shows to you that as h goes towards 0, this rectangular area becomes pretty much one and the same thing as a x plus h minus a of x. So in other words, f of x is roughly equal to this, but when we shrink h down to 0, this relationship becomes from being approximately equal to exactly equal. So f of x, what we have here, is the limit as h goes towards 0 of this change in the area function divided by h. Now what we're going to do is compare this with the result a from the tangent function, where we had f dashed of x was this limit here, which was dy by dx. So we're going to link this result to the result we've just seen with this diagram. So this is a gradient function. So let's compare this to our area function here. And so if we compare this here to this limit here, it's exactly the same idea, exactly the same in fact. X plus h in brackets, x in brackets, h on the bottom, it's exactly the same. The only difference here is, for this limit on the top, we were talking about f of x, which is y. Down here, instead of f of x, we're talking about a of x, which is our area function. And so the only difference here, oops, that's the wrong colour. The only difference we've got here is that instead of this being relating to y on top, the top bit here just relates to the area function. So instead of it being dy by dx, this will just be dA by dx. And bear in mind, dy by dx, remember y is f of x, so d f of x over dx, that's the same as f dashed. And so if dy by dx gives us f dashed, dA by dx, that gives us a dashed of x. So in other words, f of x, which equals this, which equals that, equals the derivative of the area function. So f of x is the same as a dashed of x. Now this is really crucial. So using that result and result b from the tangent function, from differentiation, we had f dashed of x is dy by dx, then y is obviously the integral of f dashed x dx, going back to chapter 13.2. So just putting back what we had here, that's dA by dx, which is the definition of a dashed of x. We can also use an analogous link to this to get something that relates to our area. And so f dashed of x, if I just replace the f dashed with a dashed, we can now say that as a dashed of x equals dA by dx, but it stands to reason that the area function must be the integral of a dashed x dx. So all I've done here is just linked f dashed of x and replaced, in a sense, the f dashed with a dashed. It's exactly the same idea, but instead of using f dashed in our limit, we've now got a dashed. And so a of x must be the integral of a dashed of x dx. However, we can go one step further here. So from this area function, we started off with f of x, linked it to this limit, which is by definition dA by dx, which is a dashed of x. So just using this here, knowing that one is equal to the other, we could even say that the area function at x is the integral of this, but because a dashed x is the same as f of x, we can now say that the area function at x must be the integral of f of x dx. And that is a crucial result. That is the main point of you listening to this for a good 15 minutes or so. That is where I want you to be convinced by this result here. So it's so important, I've just put it in red here. So as f of x is dA by dx, then the area function of x, which we'll see in a minute is the area under the curve, is the integral of f of x with respect to x. Just thinking over it in a different way, I want you to think about result C from before. Now, if you weren't sure what result C was, I'm going to remind you. Here it is. It's this result here. So instead of using h, imagine it in terms of delta functions. So if you think about this blue rectangle here, in terms of x and x plus delta x, the width of this rectangle is going to be this width here, which is delta x, and the height will be f of x. So this blue area, which is approximately rectangular, not exact, approximately, will be the area of this rectangle with a width of delta x and a height of f of x. So delta A, this tiny area, dA, delta A, is approximately equal to f of x multiplied by delta x. Dividing through by delta x gives us that the function of x is approximately equal to delta A over delta x. Then exactly in the same way as result C, if we let delta x approach 0, then the area shrinks to 0, like we showed previously. And then you obtain that f of x, this limit becomes exact, delta A over delta x becomes dA over dx in exactly the same way, for exactly the same reason as before, when delta y over delta x becomes dy over dx. Then using the same logic as before, we get the same result. If f of x is dA by dx, then the area function is the integral of f of x delta x. And again, just worth putting this down in red a second time, because that is a crucial result. That is the take-home shot there. That is what you need to know, need to remember, need to apply. Just going slightly further, I did define the area function as being between 0 and x. So what if you didn't want it to be between 0 and x, but you wanted an area between two different points on the curve, say between A and B, like we've got here? Okay, what about this instead? So the required area in yellow would be the area function at B subtract the area function of A. So the area function at B would be all of this. The area function at A would be just this bit. So big area, take away the small area, that would give us the yellow area. So this is what we'd need to calculate, which should be a bit of a pain really. Is there any quicker way of doing this? Well, yes, there is. What we can do is we can invoke the fundamental theorem of calculus from last lesson, which told us if the function f dashed is continuous on this interval between a and b, then we can integrate between the limits of b and a this function here, f dashed of x, and then we get the function at b minus function of a. Now what we can do here is link in our new limit we've been talking about previously. So not f dashed of x, but a dashed of x. And so if we replace this with a dashed instead of f dashed, then it stands to reason that if we integrate between b and a of a dashed of x, we get the area function of b minus the area function of a, which is exactly what we want to calculate. that gives us our yellow bit of the graph. But from a few minutes previously, I showed you that a dashed of x is the same as f of x, which is the same as y, if you have a curve which is y equals f of x. So just taking out a dashed x and replacing with f of x, we now have this important result here. And so we can integrate the function of the curve between b and a, and we get the area underneath that curve between the vertical lines x equals b and x equals a. So that now gives us the crucial and powerful result, which is here. The area between a positive curve, the x-axis, and the vertical lines x equals a and x equals b is given by integrating y with respect to x between the limits of b and a, where y, which is one and the same thing as f of x, is the equation of the curve itself. So again, the things in red are the crucial take-home points, this being the main thing you need to remember and apply from today. It's now just worth pausing for a tiny breather there. If you got through that bit and actually understood it, then very well done to you. Okay, apologise if I went a bit too slowly, but it really is quite important. Again, the fact that the exact area underneath a curve can be obtained using that previous result, it's one of the most beautiful things in all of maths, it really is. It holds true for all sorts of weird and wonderful functions and curves. But first of all, let's just convince ourselves that it works by integrating some simple functions and comparing the results to what you already know from GCSE work, and even earlier, dare I say. Okay, so just a few quick examples before you start off on your own. So imagine the area of a rectangle. You can do this using integration. So part A, calculate the area of a rectangle using basic maths. Part B, then integrate and find the area using calculus if you can. So pause the video here and have a go if you can do now. Okay, let's have a look at this. So the area of this rectangle using basic maths. Area of a rectangle, you obviously know, that's length times width. So that's 5 times 4, which is 20. We're going to verify this now using calculus, and so we can integrate between the 2 points 6 and 1 with respect to x. And so y is going to be the integral between 6 and 1 of y dx. Now y is just 4. So if you integrate a constant with respect to x, we just tag an x at the end of the constant term. So 4 becomes 4x. And we're going to integrate this between 6 and 1. So that's going to be 4 multiplied by 6. Not that brackets are needed, but whatever. Minus 4 times 1. So that's going to be 24 minus 4, which is 20. Which is what we had from before. So it checks out, it works as you'd expect. Slightly harder example for you to try. Again, do this first yourself, pause the video, then just check to see if you've got it the same as what I'm doing it here. Okay, so unpause when you're ready. Okay, let's go. So here we've got this red shaded triangle. So first we'll calculate this triangle using basic maths. For part B, we'll then verify it using integration. So this rectangle, we all know what the area of a triangle is. Area is going to be half base times height. So for this one, it's going to be a half times a base, which is 4 long, times a height, which is 8. So half times 4 times 8, half of 32, that just gives us 16. We can verify this using integration. So the limits are 4 and 0. Now y is 2x. So if we integrate 2x with respect to x, so 2x, the x power goes up 1, becomes 2x squared. We then divide by the new power of x, which is 2. So 2x squared divided by 2 just gives us x squared. I'm going to integrate this between the limits 4 and 0. So that's going to be 4 squared minus 0 squared. 4 squared is 16. 0 squared is just 0, so we're just left with 16. So again, this checks out too. And so the area using integration is consistent with what we know. So this is hopefully convincing you that this method for integration does work. It works for all sorts of curves, but as I've said, let's just try it now for some basic results as a little warm-up. The third one, slightly harder, but not too bad, area of a trapezium using integration. So I've made this trapezium by thinking of a function y equals 5x plus 3, and I put the limits x equals 2 and x equals 10. So calculating this trapezium using basic maths, well, the area of a trapezium is half, then add together the lengths of the two parallel sides, so call that A and B, and then we multiply by the height. So what we need to work out first of all here, if we're going to do this, is we need to work out this height here and this height here too. So we know that y equals 5x plus 3, and so down here the y value is 0. If x is 2 though, this height here will be 5 times 2 plus 3, so that's going to be a height of 13. Similarly, when x is 10, 5 times 10 is 50 plus 3, that's going to be 53. So using this formula, the area of this trapezium will be half 13 plus 53 multiplied by 10. Now for this we may as well just be sure and use our trusted class whiz. So we've got half 13 plus 53 times 10, and that gives us 330. Whoops, what am I doing? That's silly. No. If you spotted my mistake, thank you very much. No, the height is between 2 and 10, isn't it? So actually the height here, between 2 and 10, that's going to be 8. That's what you get for rushing. That's going to be a height of 8. So times it by 8 rather. My mistake. Thank God I spotted that one. Now we have 264. And let's see if we can verify that using integration. So between 10 and 2, if you integrate y with respect to x, well, y is 5x plus 3. So what we get here is the 5x becomes 5x squared over 2. So we get 5 over 2 x squared. The constant term 3 becomes 3x. And we have the limits between 10 and 2. So that gives us 5 over 2 times 10 squared, which is 100, plus 3x, 3 times 10, which is 30, minus off 5 over 2 times 2 squared, which is 4, plus 3 times 2, which is 6. And so if you try it on a calculator, or trust yourself, I'll try it on a calculator to be honest, you get 280 minus 16, which is 264, which is exactly what we expected, because that is the area of this trapezium. So I'm not saying that we would use integration and calculus to do easier things a harder way. What I am trying to prove to you is that it does work, it is consistent. It isn't just something you have to take my word for. It does work. These are ways we can convince ourselves that it does work. It also works for curves as well, which you're going to practice on now. If you could have a go for me, please. Questions 1 through to question 5, starting on page 299, exercise 13E. Do those now as almost a warm-up. We'll have a look at the next half of the exercise next time, and as well, I'll do a bit more convincing you about the methods of this integration technique for curves. Okay, thanks for listening. Well done if you got through all of that. Do practice these as ever. Any problems, drop me an email and you'll hear from me next time. Thank you very much.